Hi there, Miss Barber here. This lesson is titled Definite Integrals. We now define the definite integral, which is a generalization of the definition of area. Here, we drop the requirements that f be positive and continuous on all points of the closed interval from a to b. Definition. Suppose f is a function defined on the closed interval from a to b. Divide that closed interval from a to b into n sub-intervals of equal length. Delta x equals the quantity b minus a divided by n, with endpoints a equals x sub naught, is less than x sub 1, is less than dot dot dot, is less than x sub n, which equals b. And choose sample points x sub k asterisk, an element of the closed interval from x sub k minus 1 to x sub k for k equals 1 all the way to n. The definite integral from a to b is integral notation from a to b. F of x dx is equal to the limit as n approaches infinity of the summation as k goes from 1 to n of f of x sub k asterisk times delta x, provided this limit exists and has the same value for all choices of sample points. Some definite integral properties. For some functions, this limit does not exist. When the limit does exist, the function is said to be integrable on the closed interval from a to b. When f is non-negative and continuous on the closed interval from a to b, the definite integral exists and is the area under the curve and above the x-axis. When f is continuous on the closed interval from a to b, the definite integral exists and should be interpreted as the net area. That is, the area of the regions above the x-axis and below the graph minus the area of the regions below the x-axis and above the graph. I'll use the graph provided to discuss net area. Let's observe that the graph is located in both the first and fourth quadrants and has three smooth connected components. Reading from left to right. First component's base is along the x-axis from 1 to 2. The curve is above the x-axis with height 6 corresponding to x equals 1. Falls to 2, that portion is labeled A. The second component is between x equals 2 and x equals 4, is located in the fourth quadrant, is upward facing and parabolically shaped. The lowest point just below -3. The portion is labeled B. The third component is in the first quadrant between x equals 4 and x to 6, downward parabolic shape with max location just above 6. Let's consider net area. We'll look at the area of A. That would be the integral from 1 to 2 of f of x dx. Now let's look at the area represented by B. We would add that. So it would be the integral from 2 to 4 of f of x dx. And finally, let's consider the area C. That would be the integral from 4 to 6 of f of x dx. Replacing that integral notation with the letter that represents the area, we would write this as a minus b plus c. Notice we subtract the area b that is below the x-axis. The following theorem says that as long as the function is not too badly behaved on the closed interval from a to b, it can be integrated. Theorem. If f is continuous on the closed interval from a to b, or has at most finitely many jump discontinuities on the closed interval from a to b, then f is integrable on the closed interval from a to b.